honored. Well, thanks for the opportunity to speak today. I'd like to start out by first thanking and acknowledging my collaborators, including my collaborators at the University of Utah, as well as my collaborators at the Utah Department of Health Office of the Medical Examiner, as well as our funding sources, including the University of Utah Program for Air Quality, Health, and Society, as well as the NIH. So, suicide is a major public health concern in this country. And since 2006, this figure shows us how the rate of suicide has increased over time, while the rates of other major causes of death, including accidents, all causes of death, diabetes, and heart disease, have showed opposite declines in their rates. So since between 2006 and 2011, we saw an 11% increase in suicide, and that has not changed since. We're continuing to see similar types of increases. And the story isn't different here in Utah. In Utah, suicide is overall the 7th leading cause of death. We are part of what's commonly referred to as the suicide belt. And this largely includes most of the other intermountain states, Rocky Mountain states, as well as Alaska. Utah has the 5th highest rate of suicide in the country. And among persons 10 to 21 years of age, it's actually the 1st leading cause of death. It has a very complex etiology. The predominant hypothesis right now is that suicide is the result of an interaction between genetic and environmental risk factors. The genetic risk factors are those that have found to be both associated with psychiatric or co-occurring medical conditions. Approximately 90 to 95% of persons who die by suicide, and I'll refer to them as suicide decedents for much of the talk, but 90 to 95% of suicide decedents have a psychiatric condition at some point in their lifetime. And the environmental risk factors that have been associated with suicide include previous and current adverse life events, as well as a number of physical, chemical, and biological risk factors, which are largely fairly correlated temporally and spatially. And these include rainfall and temperature, duration of sunshine, springtime, pollen, altitude, and more recently, in the focus of my talk today, ambient air pollution. So we still don't have a great understanding of why Utah's suicide rates are high, and especially high relative to other U.S. states. And there's a couple of hypotheses that have been are being considered, and these include access to firearms. Rural population, suicide risk increase is associated higher risks in rural areas. However, as many of you know, Utah is actually considered a fairly urban state, given that 70% of our population lives along the Wasatch Front, so we don't think that that is a huge contributor. Altitude, my colleague Perry Renshaw at the University of Utah is doing research now to look at the association between altitude and risk of suicide. We experience high rates of mood disorders here in Utah. We have high rates of use and abuse of opioids, and there are other potential risk factors that are being explored that might be somewhat unique to Utah. Okay, this is an image that is very familiar to this audience. I won't spend a lot of time talking about this, but this is not uncommon in the wintertime. This is an image of a wintertime air inversion event here in Salt Lake County. A few years ago, my colleagues and I were pondering, given how aware we were of the association of these type of wintertime air inversion events with other poor health outcomes, such as increased risk of emergency department visits, increased risk of cardiovascular events, exacerbation of asthma and pulmonary disease. We also wondered if perhaps there might be an association between poor air quality and risk of suicide. So that led us to conduct our first study, which was published in 2015 in the American Journal of Epidemiology. I'm just going to briefly discuss these findings and then go on to our current study. But basically what we found was a 5% increased risk of suicide associated with an interquartile range increase in fine particulate matter, and a 20% increased risk associated with an interquartile range increase in nitrogen dioxide. And why I'm presenting this figure over here, where we have the individual pollutants on the x-axis and then the percent increase in odds per interquartile range, is to show you a pattern we observed. In this figure, each point represents either the day of suicide or the day preceding a suicide. So we've got and we refer to them as lag days. So on this graph, we show 1, 2, 3 lag days preceding the suicide. So we measured exposure on the day of suicide as well as the days preceding suicide. And what we observed is what looks like to be an increasing risk of suicide with increasing number of lag days preceding suicide for both nitrogen dioxide, coarse particulate matter, although we didn't find statistical significance, PM 2.5, but not for sulfur dioxide. So that made us think that maybe we have missed actually the peak risk associated with ambient air pollution exposure for suicide, and we hadn't gone back far enough. So that influenced the way we designed our current study. We also found evidence of effect modification, where we found strongest associations among males, persons aged 36 to 64, persons dying in the springtime, and then persons who died by violent methods of death. So we then, given these findings, we then went back to the drawing board to think about what the biological mechanism might be, what that might be involved with this association. So there are a couple of potential biological mechanisms. These include oxidative stress, hypoxia, and then inflammation. And so this figure kind of outlines how inflammation might be involved with suicide risk. Basically, there's sort of two sub-mechanisms here. There's a direct mechanism and a peripheral mechanism. Either way, what results is either direct absorption of air pollutants into the brain, or either peripheral exposure via inhalation through the lungs, which causes the release of cytokines. And both of those would lead to a whole cascade of changes in the central nervous system that could potentially lead to suicide. But we know that inflammation is mediated by genetic risk factors, and our feeling at that time was that if we don't consider how genetic risk might play a role in air pollution and suicide, then we actually may be attenuating the relationship. And so in our next study, we wanted to take into account, as I mentioned earlier, as the predominant hypothesis is gene-environmental interactions, we wanted to take this into account in our future study. And of course, here in Utah, from genetic risk, we have evidence that it also plays an important role. This is a study we're just now conducting that measures the relative recurrence risk of suicide as a function by class of relative, where we have first-degree relatives here, second, third, and then fifth-degree relatives here. And what we can see is that the risk of recurrent suicide in a family is increased or above 1 for every class of relative. The fact that it decreases, it's strongest among first-degree relatives, and then drops down towards fifth-degree relatives, this is actually evidence that genetics play a role in a risk of suicide. So this helped drive our two objectives that we had for our current study. The first one being that we wanted to replicate our initial findings by using a larger population, and we also wanted to include ozone in the current study. And then we also wanted to look to see how familial risk, which is a good proxy, so whether or not an individual belongs to a high suicide risk family, if that moderates the relationship between ambient air pollution and risk of suicide. Okay. So our study included all completed suicides in Utah from January 1st, 2000 to September 14th, 2014. This was information provided by the Utah Department of Health Office of the Medical Examiner. The suicide decedents were linked to their data in the Utah Population Database. In order to model the association, we used conditional logistic regression models. We had to consider meteorological confounders, including precipitation, humidity, average temperature, length of day, and difference in the length of day. And then we also estimated daily exposure to PM 2.5, nitrogen dioxide, and ozone, and we broke down the distribution into quartiles. And the actual method that we used in order to estimate air pollution concentration was an inverse distance weighted approach, where the estimated concentration at the suicide decedent's residential address at time of death is a weighted average of the observed concentrations around it. So we considered all of the monitors surrounding the residency in an air basin, and then used a weighted average of those measures to find to estimate the concentration of air pollutants experienced by the decedent just prior, on the day of, and days preceding their death. So as I mentioned earlier, suicides cluster in families, and this is an example. This is an extended family that's based on genealogical information in the Utah population database. For this particular family, we estimated that their familial risk using a statistic called the Familial Standardized Incident Ratio, which measures how clustered suicide is in a family based on observed versus expected counts of suicide. Their FSIR was 2.6. And that's a statistically significant heightened risk of suicide within this family. So for each suicide decedent, we linked them to their family information in the Utah population database and estimated their FSIR. And then we categorized them as to belonging to either a high suicide risk family, a not high suicide risk family, or an unknown suicide risk family. There were a number of individuals who do not link to any genealogical data in the Utah population database, and we therefore cannot make any assumptions about their familial risk of suicide. We used a bidirectional case crossover design, and the benefit of using such a design is that decedents can serve as both their own cases as well as their own controls, and this allows us to control for many individual level differences in our population for which that we are missing or don't have access to information. So the control period is identified here in this figure in red, and really what it comprises is the day the individual died by suicide as well as the days preceding the suicide of which we're interested in. So for this study, we went back, we included 1 day preceding, 2 days, 3 days, 4 days, and 5 days preceding the suicide. And then the control periods include the days of the same day of the week, 14 and 21 days before and after the day of suicide. So we compared ambient air pollution exposure in the control days versus the case day. And we fit separate models for each lag day and for each air pollutant. Okay. So a quick description of our study population. This is pretty typical, but 80%, about 79% of our suicides were male. And then we don't see big differences between males and females in terms of their distribution of age, their distribution of race and ethnicity. They were largely white, non-Hispanic. The distribution of season during which they died by suicide. The only difference we really see is that males were more likely to die by violent methods of death than females. This is also not unexpected. Very briefly, looking at the distribution of the air pollutants themselves. This is for ozone, and then And then the quartiles themselves are shown by these red lines. So we also don't observe, just based on the raw data themselves, big differences in the distribution of ozone, PM 2.5, or nitrogen dioxide. Then going on to our population-wide findings, this is represents our findings for ozone with the lag day on the x-axis and then the adjusted odds ratio of suicide on the y-axis. And so for ozone, we did not detect an association between suicide and ozone exposure. However, for fine particulate matter, we found a 16% increase in the risk of suicide associated with exposure to PM 2.5 to the third quartile. That's the highest, strongest association. Third quartile of exposure of PM 2.5 on lag day 4. But like we saw previously in our first study, it looks like we're sort of seeing an increase in the strength of the association between PM 2.5 and suicide with increasing lag day. So that also was replicated from our first study. And then for nitrogen dioxide, similar. We see a 30% increase in the odds of suicide associated with exposure to the fourth quartile of nitrogen dioxide, and that's, of course, relative to the first quartile of exposure. Okay, then moving on to our stratified analysis, we see, this is for just PM 2.5 and then for nitrogen dioxide, since we didn't find an association with ozone, that the same goes for the stratified analysis. This is the high suicide, decedents in the high suicide risk families, not high and unknown. And we found evidence of moderation by familial risk of suicide among persons in the high suicide risk families, but not in the not high and not for the individuals with unknown familial risk of suicide. Similar pattern for, and these are all for lag day 4 specifically. Similar pattern for nitrogen dioxide, 37% increase in risk of suicide among persons belonging to high suicide risk families for the fourth quartile of exposure. No statistical association there, or for the unknown group. Okay, so summarizing and a little bit of discussion about our findings. This study supports our previous work and also suggests the strongest association identified on lag day 4. In our previous study, we didn't go that far back. This adds to the increasing body of evidence that's been accumulating from very distinct geographical, cultural, and climatic areas, including China, Japan, Taiwan, and Korea, that demonstrates an association between ambient air pollution and risk of suicide. And we did find evidence of moderation of this relationship based on familial risk of suicide. This to us suggests that this is evidence of shared genetic risk factors that may mediate this relationship. So our next steps is to even further refine our FSIR familial risk groups. Can we identify the very high risk groups, the not as high risk groups, the very low risk groups, and so forth, to even reduce homogeneity even further? We want to consider other environmental exposures. We have access to pollen data for Utah, and we'd like to incorporate that into our models and examine that as a moderator. Next, we'll impute our missing air pollutant data, and then we're interested in identifying particular high suicide risk families that we can really look in detail at their molecular data to look for genetic risk factors that may actually serve as mediators of this relationship. Thank you so much for your attention today. I'm happy to, hopefully I have a minute or a couple minutes to answer some questions.